All right, let's dive into one of the most fundamental ideas in the entire universe: energy. I mean, it's literally everywhere and in everything. But here's the thing: it's also a master of disguise. It's constantly changing its form, jumping between objects. So, how in the world do we keep track of it all? I want you to think about this for a second. You drop a ball, right? It bounces. But each bounce is a little bit lower than the one before it, until, poof, it just stops. If its energy is really conserved, where did it all go? That is the big mystery we are going to solve together today. So here's our game plan. To get to the bottom of this, we're going to start with energy's one unbreakable rule. Then we'll meet the main forms of energy you see in motion. We'll look at the two big ways it gets around, through work and through heat. We'll even learn how to actually see its journey before we finally crack the case of that bouncing ball. Okay, first things first, before we go any further, you have to know this. There is one single unbreakable rule that governs every single energy interaction in the universe. I'm talking from a star exploding to a ball hitting the floor. It's called the law of conservation of energy. This is it. This is the golden rule. You can't make new energy out of nothing, and you absolutely cannot make it just disappear. The total amount of energy in a closed system never, ever changes. All you can do is move it around or change its costume. It means every last bit of energy has to be accounted for, always. So if energy is always transforming, what exactly is it transforming into? Well, when we're talking about the world of motion, we're mostly dealing with two major players on the field, so let's meet them. On one side, you've got kinetic energy. The easy way to remember this is it's the energy of doing something. If an object is moving at all, it has kinetic energy. On the other side is potential energy. You can think of this as waiting energy. It's all stored up, just waiting for its moment, ready to be converted into another form, which is usually kinetic. Now, a huge type of potential energy is gravitational potential energy. It's really simple. The higher you lift something off the ground, the more of this stored energy it has. A book you're holding way up high has the potential to fall, and when it does, it releases that energy as motion. And then there's its cousin, elastic potential energy. This is the energy you store in something when you stretch it or squish it. You know, like when you compress a spring or pull back a rubber band. It's just sitting there, waiting to snap back and let all that stored energy fly. So we've met our different forms of energy, but how do we get them from one place to another, or change them from one type to another? Well, the first big way we do that is something physicists call work. Now, in physics, work isn't about your 9-to-5 job or your homework. Work is specifically the transfer of energy. And it only happens, this is key, when you apply a force to an object and that force makes the object move some distance. If there's no movement, there is no work, period. And, of course, there's math for it. We can calculate work, which we call W, by multiplying the force, F, by the displacement or the change in position, delta X. But even more importantly, work is simply equal to the change in a system's energy, or delta E. They're really just two ways of saying the exact same thing. You know, a great way to think about this is like an energy bank account. When you do positive work on something, say lifting a dumbbell, you are depositing energy into that dumbbell. But when a force like friction slows a sliding puck down, it's doing negative work. It's withdrawing energy from the puck's account. So besides all this pushing and pulling, there's another huge way that energy moves around, one that you feel every single day, and that's heat. Heat is just thermal energy on the move. And heat moves in three main ways. First, there's conduction. That's energy transfer by direct touch, like grabbing a hot pan handle. Ouch! Then there's convection, which is how heat moves through liquids and gases, like in a pot of boiling water, where the hot water rises. And finally, there's radiation, which is energy that travels as waves, like the heat you feel from the sun, which travels all the way through the vacuum of space to get to you. Okay, so trying to keep track of all these energy changes in your head can get, well, a little tricky. But physicists have this amazing tool to help us out. We can actually draw a picture of the energy in a system using simple bar graphs. And trust me, this is a fantastic way to actually see the law of conservation in action. So let's try it out with a classic physics setup. We've got a cart, and it's smushed up against a compressed spring, just ready to launch. We're going to take a snapshot of the energy right before it launches, and then again when the cart is way up at the top of a loop. So check this out. In our initial state, just before we let go, the cart isn't moving an inch, so zero kinetic energy. It's at ground level, so zero gravitational potential energy.
Every single bit of energy in the system, let's just call it 5 units worth, is stored up as elastic potential energy in that squish spring. Okay, now fast forward to the final state. The cart's at the very top of the loop. The spring isn't compressed anymore, so that elastic energy is down to 0, but the cart is moving, so it's got kinetic energy, we'll say 2 units, and it's high off the ground, so it has gravitational potential energy, 3 units worth. Now what's 2 plus 3? It's 5! Look at that! The total energy is still 5 units. It didn't disappear, it just transformed. And just like that, we're now equipped with everything we need. We know the rules, we know the players, and we know how to track the transformations. It is time to go back and solve the mystery we started with. So what is the deal with our bouncing ball? It starts with a bunch of gravitational potential energy at the top, but by the time it stops bouncing, all that energy seems to have vanished. We know it can't be destroyed, so where is it?
The answer lies in this idea of dissipated energy. See, every single time that ball hits the ground, the impact actually squishes the ball a tiny bit, which creates a little bit of heat. Plus, there's air friction and floor friction, and hey, you can hear the bounce, can't you? That thump? That sound is also a form of energy. So the energy isn't lost, it's just transformed, or dissipated, into these less useful, more spread out forms.
Let's look at it this way. After that very first bounce, the ball shoots back up, and it gets most of its energy back as gravitational potential energy. But see that little slice of the pie? About 15% of that initial energy has been turned into heat and sound. That's energy that's not coming back for the next bounce, which is why the second bounce can never be as high.
Now, skip ahead a few more bounces and look what's happened. That dissipated energy slice has gotten huge. With every single bounce, more of that useful, organized energy is siphoned off into random heat and sound, leaving less and less available to make the ball bounce. Eventually, all of that starting energy has been dissipated, and the ball just comes to a stop. And there you have it, mystery solved. So the big takeaway here is that energy is never truly lost, it just changes form. And once you start looking for this pattern, you'll see it absolutely everywhere. From a kid on a swing that eventually slows down, to your car's brakes getting hot when you stop. So what other examples can you think of where motion stops because its useful energy is quietly turning into heat? Thanks so much for joining me today.